right, continuing our discussion, yesterday we talked about thermal energy, the sum of the kinetic energies of all of the molecules, and temperature, the average kinetic energy. Make sure you're making that distinction between the two. And today we're going to talk about heat, and we're going to begin that by looking at how I can change the thermal energy of a system. I can change it through conduction, which is the transfer of thermal energy through direct contact. And think of an example of this, and probably one that comes to mind right away, and you can write it down if you need to, is when I want to boil water. I turn on the stove, the burner gets hot. I place the pan with the water in it on the burner, and by direct contact, the thermal energy goes from the burner to the pan to the water. Conduction. Convection is the transfer of thermal energy by the movement of a fluid. Transfer of thermal energy by the movement of a fluid. And by fluid, it doesn't have to be liquid. Air is considered a fluid. So if you have, for example, forced air heat, then warm air is blown into the room, and as it moves through the room, it is transferring the thermal energy from the warm air to the things around it. So the motion of the fluid brings thermal energy into the system. And then the last one is radiation, and it is the transfer of thermal energy by electromagnetic radiation. And what's different about this, so think sunlight, that's going to be radiation. That's, you get warmed up on a summer or even a winter day, you can get a little bit more warmed up because the sun is producing electromagnetic radiation, especially in the form of infrared radiation, that causes you to warm up. So it's the transfer of thermal energy by electromagnetic, and I'm just going to make this little EM here for electromagnetic radiation. The nice thing about this form of transfer of thermal energy is that that can be done in a vacuum. It doesn't require particles. Both A and B require matter in order for that transfer to occur, but radiation can happen in a vacuum. All right, so an example of that's going to be a sunny day, warms it up because of the radiation from the sun. All right, so by definition, you're going to notice that these all have one thing in common. Transfer of thermal energy, transfer of thermal energy, transfer of thermal energy. Heat is energy transferred, or thermal energy transferred to or from an object. And I'm going to make it E thermal again. Transferred to or from an object. When would it be to an object, and when would it be from an object? How could you predict that? You're going to predict it by the difference in temperature of the two objects, or of the object in its environment. From to or from an object, because of a difference in temperature, between the object and another object, or an object in its environment. Or its environment. Let me give you an example of this. You're transferring heat. It's a super cold winter day, which we've experienced a lot of those. It's a super cold winter day, and you have hand warmers. So you open up the package of hand warmers, and you shake it vigorously to get the chemical reaction going in there. Is the transfer of thermal energy going to be from the packet to your hand, or your hand to the packet? And it's all about a difference in temperature. It's always going to flow from a higher temperature to a lower temperature. It's going to transfer the thermal energy into the colder object. So whatever is the colder object receives the thermal energy, the warmer object gives the thermal energy. So the whole thing here is it is the transfer of thermal energy. That is basically the definition of heat. Transfer of thermal energy, and it's always going to go from hot to cold. The symbol for heat is Q. That's a weird looking Q. That's not a whole lot better, but there you go. The symbol is Q, and the unit for heat is going to be, again, heat is the transfer of thermal energy. So it's all about just picking thermal energy up from one place and moving it to another. So it's still energy that I'm talking about, so I would predict that the units are going to be joules. The units are joules or calories. And just so you have the conversions here, 1 calorie is equal to 4.18 joules. And also you will see it in the imperial system as the BTU, British Thermal Unit, and a BTU, 1 BTU, British Thermal Unit, is equal to 1,055 joules. Right, so these are my basic units, joule or calorie. You're going to see those most often, but then in the imperial there's also the BTU. Heat and thermal energy are used interchangeably, but technically there is a difference between them. And so in this chapter, I'm going to fuss if you use thermal energy for heat or heat for thermal energy. Heat is defined relative to a system. And by that, it's either going into the system or it's going out of the system. Heat is defined relative to a system. Thermal energy is just the sum of the kinetic energies. Defined relative to a system. Heat is also energy transferred, thermal energy transferred and if I am talking about it relative to a system, it's going to be transferred between the system and the environment. And the formula is going to be W plus Q is equal to a change in the energy of the system. And it can either go into the system or it can go, if the system is a higher temperature, it could go out of the system into the environment. All right, so heat is the transfer of thermal energy. It is the transfer of thermal energy. Thermal energy is the packet of energy an object possesses. Heat is if that packet of thermal energy is transferred to something else or more thermal energy is brought into it. That is heat. And we're going to measure all of the ability for it to transfer in something called specific heat capacity. And I want you to think of specific heat capacity as the idea of how hard or how easy is it to transfer the thermal energy to or from that object. Does it go easily or does it go a little less quickly? It takes a lot more time and energy, not energy, I don't want to say that. It takes a lot more time for the transfer to occur. Specific heat capacity kind of measures that in an object. And you've already learned this probably in chemistry, but it's the amount of heat, so I'm transferring thermal energy, that must be added to a unit mass of a substance Notice I've said unit mass. I haven't said gram, I haven't said kilogram. I've just said a unit of mass of a substance to raise its temperature by 1 degree Celsius. And it's always Celsius. Not Kelvin, not Fahrenheit. So it's always Celsius, but may not always be grams. It could be kilogram instead. All right, so C is that measurement for it. It's what tells me how capable it is. C is the unit or the symbol for specific heat capacity, and I showed you that here. It's a symbol for specific heat capacity. And C is measured in joules per kilogram degree Celsius, always degree Celsius, or it could be calories per gram degree Celsius. Notice that the kilogram goes with joule, which you kind of would have predicted because a joule is a Newton meter. A Newton is kilogram meters per second squared. So if I'm going to have joule, I have to have kilogram. Calorie, however, is based on the gram. It's a much, much, much smaller piece. And little letter C, what type of material is going to have a low specific heat capacity? A low specific heat capacity means that it transfers the heat in and out relatively quickly. It raises the temperature with ease. I don't need to put a lot of heat into it. I don't need to transfer a lot of thermal energy in order to raise the temperature. So think about what heats up super fast. What heats up super fast is, oh no, I need to tell you something else. I'm sorry. Let's finish this. Type of material that has a low specific heat capacity is going to be a metal. They heat up super fast. They cool down super fast. Low specific heat capacity. It does not take a lot of energy. It doesn't take a lot of heat to raise a gram of metal 1 degree Celsius or a kilogram of metal 1 degree Celsius. Low specific heat capacities are metal. B, something about C that you need to know. It is a constant. For a given substance. It's not a universal constant, it is substance specific. Okay, let's make that given substance. Now how this works in actually determining if I have this much of this material, what is going to be the heat that I need to raise the temperature, or what is the temperature that I'm going to raise it if I have this much heat. The formula that I need for that is Q, which is heat, is equal to M, which is mass, C, the specific heat capacity, delta T, how much do I want to raise the temperature. Q is equal to MC delta T. And you'll see then why the C is joules per kilogram degree Celsius, because I need to have joules on this side, so I have to have joules on the right side as well, but I need to get rid of the kilograms for mass, so that's in the denominator here, and I need to get rid of the degrees Celsius here, so that's also in the denominator here. And you will find on the first page of this chapter all of the specific heat capacities on one of the charts or one of the papers that are listed in the items that you need for this chapter. Specific heat capacities is one of those documents. All right, let's actually put this into a problem. A 30 kilogram child has a temperature of 102.2 degrees Fahrenheit. How much heat must be removed to lower his temperature? So I'm taking heat out to lower his temperature to 98.6 degrees Fahrenheit. I want to lower his temperature. Now the problem is I have degrees Fahrenheit and degrees Fahrenheit here. All of my specific heat capacities are based on degrees Celsius. First thing I have to do is convert from degrees Fahrenheit to degrees Celsius. So my delta T is T minus T naught, so 98.6 minus 102.2, which is a negative 3.6 degrees Fahrenheit. Now to make the conversion, I'm going to just pull out by what ratio is it different. So this is how I would do this one. Degrees Celsius then is going to be negative 3.6, and the ratio of difference between Celsius and Fahrenheit is 5/9. So my degrees Celsius then is going to be a negative 2.0 degrees Celsius. If you're having a hard time seeing this, let me know, and we can talk through where that came from. And C for water, C for the body is 3,470 joules per kilogram degree Celsius. And again, that's on that document of constants that is on the first page. Now I put it into the equation. Q is equal to mc delta T, and it's going to be equal then to 30 times 3,470 times my delta T, which is a negative 2.0. My answer then is going to be a negative, which indicates I'm pulling heat out, not putting it in, 2.08 times 10 to the 5th joules. All right, that's the application of Q is equal to mc delta T. Again, if you're confused about how I just was able to use the ratio instead of adding or subtracting 32, let me know, and I'm happy to show you that. But when I'm trying to convert change in temperature of Fahrenheit to change in temperature in degrees Celsius, I just use the ratio rather than the plus or minus 32 added on to it. All right, your homework I will post on PowerSchool. I don't have that in front of me, so I'll post that on PowerSchool with this. Let me know if you have any troubles with this, but this should be pretty straightforward. And by the way, I tend to talk a little bit extra at the end of this because, for whatever reason, when I shut this off, it clips the last couple of minutes of the video. I'm sure I've told you that before, but I just want to remind you, I'm kind of going on and on right now, just so that we get at least the last